Steinhauer here. Welcome back. We are moving on to chapter 26, which is when we're going to talk about galaxies as a whole. So we're taking our cosmic zoom lens and moving it ever wider now to think about larger and larger structures in the universe. We've talked about the Milky Way already. Let's think about how the Milky Way is similar to and different from other galaxies in the universe, and how understanding galaxies can lead to understandings of even bigger structures like the universe. And that leads us right to this. Galaxies and the universe itself are intimately connected because galaxies are the main constituents of the universe. They are the basic building blocks, sort of the largest single structures, entities in the universe. And so understanding galaxies is fundamental to understanding the universe as a whole. And understanding the universe as a whole is a topic that we're going to be covering for the last few weeks of the class. Specifically, the study of cosmology, the study of the cosmos, the study of the universe as a whole, the study of the structure and evolution and beginning and evolution and eventually end of the universe itself. And that's sort of a preview of where we're going to be over the last few weeks of the class. But let's start with galaxies. And let's start with one of the most important images that was ever taken of the sky, really. This is the Hubble Deep Field, and the origins of the Hubble Deep Field are fascinating. The Hubble launched in 1992, and for the first couple of years of its life was hindered by a rather tragic and horrible optical flaw in the mirror, which caused all of the what was supposed to be an extremely powerful telescope for getting very high resolution images to be much less than ideal. That problem was fixed a couple of years on by a successful and very long and complicated mission by an astronaut crew with the space shuttle. But anyway, one of the first years after it was fixed, the director, and this is a time when the Hubble Space Telescope is vastly oversubscribed, which means that roughly of every 10 proposals that were written by prominent professional astronomers at the time to use the Hubble Space Telescope, only about one of them was accepted for actual observations. And so this was a very sought after instrument. It was highly oversubscribed. It was very difficult and very valuable to get time on this telescope. And the director of the Hubble Space Telescope at the time had a perk that went with the job. And the perk was some director's discretionary time. And he got about a full day's worth of observing, which was a tremendous amount on this brand new, very powerful instrument. And he decided in one of the first years in 1995 that he was going to spend the entire part of his director discretionary time to look at the most boring patch of the sky that he could possibly find. And here it is. Here's a zoom in. This is Ursa Major. This is the Big Dipper. And you can see it here, the handle and the bowl of the Big Dipper. There is a blank spot right there. If you zoom in on that blank spot, you get this picture. If you find another blank spot on there, this is the most boring patch of the sky he could find. There is nothing here. And he just let the Hubble Space Telescope integrate, look at this one spot, and integrate in several filters for hours at a time. And what he got was called the Hubble Deep Field, and it was the deepest image of the universe that had ever been taken to that point. Almost every object in this image is a galaxy, and it paints a different picture of the universe than we normally see, which is that this blank region is just blank. In fact, every spot we look at in the universe, in the sky, is just filled with galaxies. And this is a particularly good one to look at those galaxies because there happen to be really not many foreground stars at all between us and them. And so this is showing us an evolution of the universe in this one picture. Because remember how in astronomy we have an advantage of being able to look back in time. Right? The further away we look in space, the further back in time we look. Remember, the sun is 8 light minutes away. It takes light 8 minutes to reach us from the sun. So we're not seeing the sun as it is now. When you look up in the sky, although don't look at it, we're seeing the light that left the sun 8 minutes ago. We're seeing the sun as it was 8 minutes ago. The closest other star to us is Alpha Centauri in the southern hemisphere. It's 4 light years away. We're seeing that star as it was 4 years ago. As you get further and further away, you're seeing further and further back in time. The Andromeda Galaxy is 2 million light years away. We're seeing the Andromeda Galaxy as it was 2 million years ago. If you go back further, if you see farther, you're looking back further in time. We can push this almost all the way back to the beginning of the universe. And that's what this image started to do. It was so successful, in fact, that several years later, about a decade later, they spent an entire week looking at an even more boring patch of the sky. And this, the Hubble Ultra Deep Field, is still one of the deepest images of the universe that's ever been taken. And it's breathtaking. Just look at all these galaxies. They come in all sorts of flavors and sizes and colors and morphologies and histories. And you can study the evolution of galaxies just in this one image. There are nearby galaxies. There are extremely distant galaxies that are galaxies in this image that are 12 billion light years away. And the universe is only about 13 to 14 billion light years away, light years old. The universe is only 13 to 14 billion years old. So we're looking back almost to the beginning of the universe. So this is a good place to start our conversation about galaxies, because pretty much every kind of galaxy is represented in this picture. Let's just take a look at a few of them. Here is a beautiful spiral galaxy. You can see there's a lot of spiral galaxies spread throughout this image. If we zoom in on that guy, we see the makings of a typical spiral galaxy. There's a nice disk component. That disk component is segmented into spiral arms, and you get all sorts of wispiness and clear evidence of star formation. It looks a lot like what we think the Milky Way galaxy would look like if we could zoom up above it. But there's other kinds of galaxies as well. We've already learned a little bit about spiral galaxies. There's other kinds of galaxies that look nothing like this. Let's take a look at this galaxy. It's got a foreground galaxy in front of it, but look at the red object behind it is just a kind of fuzzy patch in the sky. There doesn't seem to be any disk component. There doesn't seem to be any bright spots or nebulas. It's just a mass of stars. And this is what we call an elliptical galaxy. In fact, there's at least 2 of them in this picture. There's the big one that you see here, and there's a smaller one off to the side. You'll notice these have vastly different colors. This is a very red object, whereas the spiral galaxy was much more yellow and blue. And the morphologies are fundamentally different also. We'll talk more about that. So you can basically break most galaxies up into elliptical or spiral galaxies. However, there's some galaxies that just defy classification altogether. And here is one of them. And sometimes galaxies just look weird for various reasons we'll talk about in a bit. But if it doesn't fit into the typical elliptical or spiral galaxy or somewhere in between, then we group it into a category of galaxies that is the irregular galaxies. Okay, we'll come back in the next video and break down some of the morphological and other fundamental differences between these types of galaxies, and maybe even think about what causes some galaxies to look like spirals and some galaxies to not look like spirals. See you then.